Okay, what we're looking at is a B&K1477. I've taken you through these scopes in the past, so this may not be anything new to you. But this is a new scope for me. It's a 15 megahertz scope, came in kind of bad shape. Um, Worked hard to get these switches cleaned, get the tarnish off of them, get the pots lubricated, get the whole thing calibrated and working well again. A couple of the switches, like the triggering and the magnification, didn't work, but they do now. And then the case was quite a mess. So I went ahead and gave it a good coat of paint, Rust-Oleum Almond. Very nice color for a B&K scope. It matches the front panel knobs extremely well. And they did a pretty decent job on the paint. This unit looks new, so I'm proud of that. And works new too. I'm going to take you through some of the features, and let's just take a look at it here. First of all, we have position controls. We're on channel A at the moment. Position controls work very fluid, nice and smooth. And then we have the input, AC, DC, and then ground in the middle. Range switch, we have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 position range switch. Even in its most sensitive setting, 0.01 volts per division, as I move the switch from one range setting to the other, you'll notice that the position of the line remains the same, and that's all part of the calibration. So this unit has been calibrated. We have a mode switch. We can look at channel A, channel B, the combination of both, A plus B added together, or A minus B subtracted waveform wise. We right now have just switched to B. I'm going to show the position knob works very smooth again. We're going to take ourselves from the most sensitive setting, and I'm just watch the line. You saw a little hop, but it didn't move. That line stayed right on. That's because of the cal again. The input switch, AC, ground, DC. We already looked at the position. We have intensity. Let's go ahead and just take a look at both traces. And we can take the intensity and take it down, bring it back to within viewing location, and then we can take her all the way up to max. Let's take a look at that with a waveform on it. Okay. Off. Viewable. Maximum intensity. Back to a viewable level. Focus. Soft blur. Other direction, soft blur, and in the middle we have focus, clarity. We can take our slope from positive to negative, back to positive. We can trigger on channel A, we can trigger on channel B, or we can go to an external trigger, which comes in on these terminals right here. If, as the frequency gets raised, I'll do that right now just to demonstrate it. You can't see the individual cycles very well. Even if you were to hit the maximum, still very difficult to see. We can pull out the ×5 magnification control, and voila, there they are. Okay. That right now is running at about 10,300,000 cycles, just 300,000 cycles. And then back. Let's go ahead and take ourselves down to something a little more reasonable. Okay. And We have an illumination for the grid. It does work. There is light in there, but to be honest, I don't see that it makes a heck of a lot of difference with this. Both lights do work. And then the sweep time, which is also calibrated, and we'll run through some tests on that in a moment as well. Then there is finally an XY position, which at the moment we see the circular Lissajous pattern because we have the same input on both channels. Okay, so let's go ahead and take this thing through some of its tests, and we'll get started in a moment. Okay, we're going to begin the time-based check here, and we're doing it at 50 milliseconds per division. And at this point, I'm feeding in a signal that's 50 milliseconds wide. So we're getting one full cycle in a division. This should mean that we would get 5 full cycles, in 5 divisions we have a full cycle. That's what this would mean. So if I start, here, I should come across, come up, over, and down again in 1, 2, 3, 4, 5 divisions. In this case, I'm doing it in 1 division. Okay, let's go ahead and step the frequency up 20 milliseconds. And in this case, we see a cycle in a division. If I pull the times 5 again, so we get a good look at it. Position myself. I see at 20 milliseconds a division. Then I should times 5. I get 5 divisions. So 1, 2, 3, 4, 5, and I should complete my cycle. Looks like I'm maybe hanging over a hair. But it looks pretty good. Okay, and step it up again. This is 10 milliseconds a division. And right at the moment, okay, here, let's turn that up. We have a cycle being completed in every division. Begins, ends. If I step up, if I go to one millisecond per division, and I look for a complete trace, then I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and end. Which would be right, because I'm running at 10 milliseconds a division. In 10 divisions, that'd be, I'm sorry, at 1 millisecond per division. In 10 divisions, I'd have 10 milliseconds, and that's what I'm displaying, a cycle in 10 milliseconds. If I was to go to 2 milliseconds per division, I should do this in 5 divisions now. So let's try and check this out. Here's 1, 2.5. There's 5. If I go to 5, I should be doing this in 1. I'm sorry, in 2. It would be 5 milliseconds per division times 2 is 10 milliseconds. And I do 10 and 2, so there we go. That's right. Okay, let's kick her up another. We are now running 5 milliseconds a division. So in 1 division, we are on the 5 millisecond per division mark. So we should see 1 full cycle. Start, end, in a division. Now if I go take this up to 10 milliseconds per division, that's double. So it should now take me if I was 5 milliseconds per division before, and I had a 5 millisecond signal, and I am now sweeping at 1 millisecond per division rate, then I am going to take 5 divisions. So here's 1, 2, 3, 4, 5 divisions for a cycle. Pardon me while my thoughts get caught up here. Let's go ahead and come back down. We're going to go up on the generator, where the generator is sending in a 2 millisecond 2 millisecond period signal, and we are on 2 milliseconds per division, so we're going to have it displayed in 1 division, which it is. And if I go to 1 millisecond, we should be displaying in 2 divisions, and it is. Here's 1, 2, perfect. Okay, let's go up again. 1 millisecond per division. And we're seeing it in 1 division. If I go to 0.1 millisecond per division, we should take 10. Here you can see the top edge of this one. We're going to take 10 divisions for that cycle. And there we're centered. Here we are at the beginning. Here we are at the end. It takes 10 divisions for that complete cycle. Let's go to 500 microseconds per division. And we're back here. Here we are in 1 division. Looks right. And if I go to 0.1, we should do it in 5 divisions. Here we're centered. Here we are 1, 2.5. 1, 2.5. That's 5 divisions. Okay. 200 microseconds per division. And we'll go back. There's the 200 microseconds. This is per division. We get a 200 microsecond signal coming in. So we do it in 1 division. 1, end. Okay. If we go to 0.1, we should see it in 2 divisions. We do. Okay, we are on 100 microseconds per division. And we are also feeding in 100 microsecond signals. So there's 1 division. If I go to 50 microseconds per division, we're going to take 2 divisions to do that. So here we are, 1, 2. Okay. We are now on 50 microseconds per division. We do this in 1 division, 50 microsecond signal and 50 microseconds per division. And we will go to 10 per division. We should count 5. So if we're centered properly here, 1, 2.5, 1, 2.5, that's 5. Okay. And then 20 microseconds per division. We should see it in one division there. Yes, we do. If I go to 10, we should see it in 2. 1, 2. Perfect. That's the end of our little calibrator here. We will switch to the PTS signal generator. Pardon me a moment. Alright, we're connected to the PTS frequency synthesizer now. We are feeding in the lowest signal that this thing's capable of, which is 100,000 hertz. Signal's not the most, it's not the cleanest sine wave I've seen at this frequency, but it's accurate. We are right now running 10 microseconds per division, and that would be 100,000 cycles per second. So we should see one cycle in every division here. And if we carefully position this thing, let's see. And all right, we see ourselves start right here, peak up, come down, come back, and that's on all in one division, so it's perfect. If I was to expand this thing by a factor of 10, we should see this thing begin and then end in 10 divisions, which it does, but like I said, it's distorted. We'll get past that. Let's go to 5 microseconds per division. That would represent 200,000, a signal of 200,000 hertz. And again, we see a cycle in one division. This is as it should be. And we also see that it takes 10 divisions to complete a whole waveform. Okay. Let's go to 2 microseconds per division. And that would be 500,000 as a frequency. And we are now one division. We have a full cycle. If I go to 1 microsecond per division, we now should take 2 divisions for a full cycle. Let's start here, right there. Here we swing negative, positive, and then we end up in 2 cycles. We're right on the division, so we're running very accurate. Let's now go to 1 megahertz for a rate. Okay. And we are 1 microsecond per, 1 microsecond per division. So it takes 1,000,000 hertz to run through here to fit 1 cycle in every division. And that's exactly what we have. Start right in the center here, swing positive, come down, and then hit up right on the line. If I was to go to 0.5 per division, we should take twice as long. So here's, we swing negative, and 1, positive, and then back down in 2. So there's 2 divisions because we're running 1 megacycle. And then my last range setting, which we're in right now, is 0.5 microseconds per division, and that would be 2 megacycles. Okay, we can kick our intensity up just a hair to make up for the frequency that we're running at. There we are, 1 full cycle in a division, just as it should be. And at this point I can pull the ×5 magnifier, and in 5 divisions I should see one full cycle. So let's do this. Okay, there we are, 1, 2.5, 1, 2.5. 5 cycles, 1 division. I'm sorry, 5 divisions, 1 cycle. There we go. Didn't know I was dyslexic. So that's all of the ranges. The time base is accurate. That we wind up now in the XY position, which we'll take a look at here. Okay. Right now, we have a Lissajous pattern. It's a circle. That's because we are feeding the same signal in on both inputs, and that would be the pattern expected. Okay, so let's take a look now at the DC voltage levels and ranges and see how that goes. Okay, just having to think about this. One of the items that we missed was the calibration point for the probe on the scope. It produces a square wave, roughly 1,000 hertz, and about 1 volt peak to peak. And right now I am coming through this brand new probe, which, by the way, you will get 2 probes brand new with this unit. This is one of them. And in this probe is a calibration point. So with this signal on there, I'm going to insert a screwdriver, and I'm going to turn this little screw, and that allows me then to adjust my probe for signal. That's, oh, okay, that's over adjusted. That's under adjusted. We want the squarest wave we can get, so we adjust it to give us a very nice square wave. Let's see, that would be about it right there. So that probe is now properly calibrated, and our probe cal test point is working fine. Now let's use this probe with our analogic DC voltage standard up here. We're going to step some DC voltages through this scope and observe the steps and show that the scope accurately reads the voltage. We've now made the connection. My probe is in the ×10 position, and that means we're dividing our input signal by 10. I'm going to zero this thing down here, and I'm going to put myself on the lowest setting. So I'm on 0.01 volts per division. So if the scope sees 0.01 volts or 10 millivolts, then it's going to jump 1 division at this point. But I've got the probe dividing the input by 10. So in order to get 0.1 on the scope, I have to put in 0.1 off of my analogic. So we're going to go ahead and I'm going to step this thing from the 0.1 position. So here we go. 0.1, 2, 3, 4, 5, 6, 7, 8. That was great. Okay, so let's go ahead and we're going to go to the 0.02 per division. Okay. Now if I want 0.02 here, that means I have to put 0.2 in, so I've got to go 2 steps up here in order to make 1 division. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now that was 10. That's 1 volt. So if I put 1 volt in there, then we can pick off from that point and go 11. Okay, there's the next step. 12, 13, 14, 15, 16. So that would represent 1.6 volts divided by 10 would be 0.16, and we are on the 0.02 per division times 8 divisions is 0.16, so perfect. Let's go to 0.05. Alright, now I want 0.05 at the scope. I'm divided by 10. That means I have to go up 1/2 of a step at a time in order to see the jump a full division. So here we go. 2, 3, 4, 5. It would be 1 division. 6, 7, 8, 9, 10. There's 2 divisions. Now if I add a volt, that'll jump another 2 divisions. And then another volt would jump another 2. And then finally another 2. So we just jumped 4 volts. 0.05 volts per division times 10 would be 0.5. Times 8 would be 4 volts, and we have 4 volts going in, so that would be right. Perfect. Alright, we go to 0.1 volt per division. I think at this point I'm going to go ahead and make my probe go to times 1. Now we're direct. And I should be able to hit the 0.1 volt per division from the standard, and we'll see go up 1 division. So here we go, 1 division. There's 0.1 volts, 0.2, 3, 4, 5, 6, 7, 8. Perfect. 0.2 volts per division. Okay. If I go 1, 2, there's 1 division. 3, 4 is 2 divisions. 5, 6, 7, 8. Okay, we got 4 divisions. 9, 10. And then if I pull in my volt knob here and go up a volt at a time, we'll jump 2 divisions. So there's, oops, sorry, I guess I miscalculated. Let's try that again. 1 volt would be 5 divisions. Sorry. So we'd have to do it from here. So I will hit the maximum if I apply 1 volt now. There we go. So that's 1.6 volts that I've applied from the analogic. Divided by 10 would be 0.16. I'm sorry, we're going straight through. We're not dividing by 10 now. Let's try this again. We're at 0.2 volts per division times 8 divisions is it's 1.6 volts. And I am feeding in 1.6 volts from the analogic. We have that perfect. Okay, let's take it back down again. Alright. We're now on 1/2 volt per division. And I'm going to take myself up 1 volt at a time. We'll jump 2 divisions. That's 1 volt. 2 volts, 3 volts, 4 volts. So 8 divisions times 0.5 is 4 volts, and that's exactly what happened. Okay, let's go to 1 volt per division. Go up 1 division, that's 1 volt. 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, we go 2 volts per division, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And we could actually, yeah, that's 10, that's as high as my My calibrator will handle is 10 volts, so if we can get 5 divisions, that's great. Let's switch to a different calibrator at this point.